Welcome to another exercise in a workbook statistics. This time with an exercise focusing on coefficient t-test and f-test for model quality. So let's have a look at the exercise. Here we have for 5 students the final grade and the number of exams they failed during their studies. That's summarized in this table. So the first row with information gives us the grade, dependent variable. The second, the exams. And the last one is an additional information. Here we assume we already conducted a linear regression and estimated the value y. That's the y hat. That's the estimated value using the regression line. And then we square those estimates. That's something we're going to need later on. And well, our task in this regard, to work with this table, first off, calculate the coefficient of determination, r squared. And then conduct a suitable test to check whether the model, for which in A the coefficient of determination has been calculated, has a significant explanatory power. We assume a margin of error of 5% and have to compare this how the results for 5% differ from those for 1%. Well, let's start with the calculation of r squared. For this one, we're going to take the table as we've been given it, and we're going to add one additional column here. And in this column, I'm going to report the averages. So for the grades for Y, for the exams for X, I'm going to calculate the average, and similar for the squared prognosed values. Then I'm going to add one more row as well, and that's the squared Y values, also with the average. Because then we have everything we need to actually use our general formula for the r squared, which is just the average of the squared estimated values, so that's the 3.4004, minus the squared average of y, that's actually here, 1.83 squared. We divide this by the average of y squared, that's here, the 3.5345, minus the average of y squared. So that's again the same thing as up here. So in the end, the only difference is here we're using the squared estimated values. Here we're using the squared original values. Well, if we are going to calculate this, we get as a result 0.2776. That's then our r squared. That's our coefficient of determination. This tells us that our model can explain roughly 27.76% of the variance in Y. Well, to know whether this is enough to be considered that the model has explanatory power, that the exams decently well estimate or are determined for the final grade, we're going to conduct an f-test as well. In the f-test, we first need to calculate the test statistic, but we already have everything we need. We have the r square from part A. We have the k. The k is just the number of x variables. Here we only have 1. Then we can also calculate 1 minus r squared, so simply 1 minus this value, because of that one. And we have n minus k minus 1. N is the number of observations, k was 1, so 5 minus 1 gives us 3. So putting this double fraction into the calculator yields an f statistic of 1.1528. This one we are then going to compare to respective reference value or reference statistic we get from a corresponding table. So here the reference statistic is k, that is the 1, n minus k minus 1, that was the 3, and 1 minus alpha. Well, in the first part we have to use an alpha margin of error of 5%, so here we get 1 minus 5%, so 0.95. If we look this value up in the table, we find a value of 10.128. We're going to compare then this reference value this test statistic, and we see that the test statistic is much smaller than the reference value. This means we have to retain H0, meaning our model does not have significant explanatory power. Well, now the question also was, what if we actually change our acceptable margin of error from 5% to 1%? Well, this would make the test much stricter, meaning if we cannot reject H0 at 5%, we will never be able to reject this at 1%. So the result that the model does not have significant explanatory power will still remain the same. We will get a much larger reference statistic, but the end result will still be the same. Well, that's maybe everything there is to this exercise. The last part, well, we could also look up the reference value, but we do not actually have to do this because we can infer from not being able to reject this at 5% also that we cannot reject this at 1%. So that's everything there is to this part, to the whole exercise. I hope you enjoyed it. I say goodbye and see you next time.